NCBM 0324, Section 1.5, Basics of Factoring Polynomials, Part 3. So that GCF is going to be very important. It's going to be our first step in completely factoring a polynomial. So finding that GCF is going to help make the rest of the process go a little smoother. Now, in the idea of a GCF, right, figuring out what is that greatest common piece, we're going to end up undoing a property that we have already been using quite a bit. And that property is the distributive property. So we've been using the distributive property to get rid of parentheses. We've multiplied a negative in or a value all the way through. But now we're going to think about this in the reverse direction. So if I have A times B plus A times C, they both have A in common. Well, I'm going to undo that distribution of A and bring in my parentheses back into place. So I'll have A parentheses, B plus C close parentheses. So that undoing of the distributive property, that's what a lot of factoring the GCF is going to entail. Now a reminder that not all polynomials can be factored, and if they are not able to be factored, we call them prime. So there will be some situations where there's nothing in common. There's no other way we can rewrite this as a product of pieces. It's just going to be prime itself. And the importance of factoring. You've seen this perhaps already in your 1324 class, but the factoring really helps us find a lot of important information, especially about functions. So we can use them to find solutions of functions, which is another way of saying zeros, x-intercepts for a graph. If I need to graph something, finding those x-intercepts is really helpful, and that can involve factoring. And also roots. Roots is another name for these x-intercept zero solutions. So it's important to have a strong foundation in factoring to help with other more complex calculations later on. Okay, so with all that, let's start factoring some polynomials. Well, the first step we're going to take in any one of our factoring problems is we're going to look for that GCF. If, of course, it's different than 1. Maybe they don't have anything in common, and that's okay. But I'm going to always look out for that GCF because it makes things nice and easier. In example 6, we're asked to factor each expression. So factor each expression, we're going to do this as much as possible, factor it as far as possible. So in part A, we have 8x minus 4. So looking at my terms, 8x is one of my terms. The subtraction of 4 is my other term. I want to look for the GCF, the greatest common factor between these two pieces. I can already tell it's not my greatest common factor is not going to have a variable in it because the 4 does not have an x on it, but the 8 does, so no variable. Let's look at the numbers. What factor do 8 and 4 have in common? If I do a quick little tree here, well, 8 is 2 times 4. 4 is 2 times 2, so my prime factorization would be 2 times 2 times 2. And if I do the same thing for the 4, well, that's 2 times 2. Right? We can see that they both have a couple of 2's in common. And what is 2 times 2? Well, that's simply 4. Right? Maybe you still need the factorization trees. Maybe you saw that right when the beginning of the problem, that I can divide both of these numbers 8 and 4 by 4. Whichever place you're at, you end up in the same value, right? You end up in the same answer. So it takes a little time if you're starting off factoring, from the very, very basics, but you have those skills. You have the ability to find those GCFs. So I'm going to erase this here, give us a little more space. So 8x minus 4, my GCF is 4. So I'm going to write the 4. I'll say 8x minus 4 is equal to 4 is on the outside. So here's my distributive property. I'm undoing the multiplication that would go in. So if I'm undoing the multiplication, what times 4 gives me 8, or what is 8 divided by 4? Well, that's 2. And then my x is still on there. I'll do the same thing for my last term. We have minus 4 divided by the 4 that I'm taking out gives me, gives me 1. There we go. Gives me a 1. So here is my factorization. There's nothing else we could have pulled forward. No other way of expanding 2x with that minus 1. That will be our factorization here. Now, a nice thing though, sometimes we may worry about our answer. It's looking a little too weird. It's just, I'm not quite certain about it. A really nice thing about factoring is we know how to undo factoring. In fact, I think we do that a little bit more. So if we were describing the distributive property as going the opposite way, but if I want to check something, I can always take that multiplication and put it all the way through. And if we did this correctly, we should end up where we started here. So factoring is almost like the opposite of that distribution property in this case. So that's kind of helpful. That's a little reassuring that if I ever get an answer, I'm just not positive, I can always check it. I have a way of checking. Okay, let's try part B. We have 6x plus 15y minus 24. So greatest common factor, GCF, is what I want to look for. So greatest common factor. What number is a factor of each of these? What number can I divide into each of these all beautifully? Well, maybe it's 6. 6 is kind of small compared to the other two, but 6 goes into 24, yeah, but 6 doesn't go into 15. Maybe something a little bit smaller. Without doing my trees, though, just looking at my numbers, I can say that 3. 3 goes into 6, 3 goes into 15, 3 goes into negative 24. So with experience, you can kind of see these GCFs a little bit quicker as you work, right? But if you need those factor trees, continue to do them. That's okay. So then my expression that I'm trying to factor, 6x plus 15y minus 24. My GCF, we said, was only the number 3, right? Even no variables, because this has a y, this has an x, this doesn't have anything. This expression, once I factor out the 3, undo the distributive property here. Let's see, 6 divided by that 3 gives me 2. The x is still there. Plus, let's see, 15 divided by the 3 is 5. And then the 24 divided by 3 gives me the 8. And there it is. Here's my factored expression. Can't do anything else. Notice 2 and the 5 are prime, so there really wasn't anything else I could do even with that 8. Last one, part C. 4x minus 3y plus 19. 4x minus 3y plus 19. So all my variables are different. So my GCF, it's not going to have any variables in it. Let's consider the 4, the 3, and the 19. Well, 3 is prime. That's one of our easier primes to remember. The only factors of 3 are 1 and itself. But I know 3 does not go into 4, so that's not going to work. The 19, well, that's also prime. The only way to multiply to get 19 is 1 times 19. And then the 4 is 2 times 2, but these aren't even. So it looks like our GCF is simply the number 1. Right? Number 1 is the only factor that works in all of them. And while I could, if I wanted to, write out 1 like this, right? Factor out the 1 in the front, that's really no different than simply writing the same thing, because 1 times anything, right, remains the same. So in this case, my factorization is what I originally started with. This expression is what we call prime. There's no other factoring to do. All the numbers and variables and terms are different. There's no factoring that we could break it down into. And that's okay. That is a possibility.